works. And we could pluck those out. They're very carefully delimited in the code. And I've pretty much kept everything I could outside, and I put it. Okay. All right, we're going to go on. And don't worry about the pace we're going. It just gets increasingly opaque as we get into this.
So we're going to slow way down.
This is the ARC fraternity hazing.
Okay, one thing is, I mean, a lot of stuff is on the slides that I've already gone over effectively. But it'll take a while to sink in anyway. So what is it? And so here it is, periodic insulation. We've already talked about all this stuff. It could be any object. In fact, lately I've been running asteroids for people. One of the interesting, side issue, one of the interesting versions of KRC, which is defunct, and I do not intend to recover, was a version for comets that took care of the coma. And you're going to love this, guys. The surface, as the surface sublimed away, the grid moved down into the object, keeping track of the temperature profile as it went. This was, I think, probably the first ever thorough model of comets. Now there's a couple of groups that just specialize in this stuff. Anyway, it's pretty good for airless bodies. And there are a lot of them, so it works for them. As long as the airless body is more than a few centimeters across. Okay. Up to 37 latitudes in a set. This number, almost all these numbers are firm coded in one place. If you change them in one place, they propagate throughout the entire KRC system, which is one of the aspects of the way this thing is coded we'll get to. Up to 2 layered materials, any total depth. We've got that, we've got that. Second order dusty atmosphere, or no atmosphere. We've got that. What's not in the KRC? This is an infinite list. Here's a few of the things that are not in KRC. It's not a radiative convective atmosphere. There's no turbulent mixing with wind speed and roughness and all that stuff. More than 2 materials of fully flexible layer. See this little light purple? This is not unreasonable to stick in. It would take some thought about how to solve the equations initially, but then the essence of the code would be the same. Vertical transport of sensible and latent heat by gaseous diffusion. Quite a few people have addressed this because they're worried about the history of ice on Mars, which is a big issue. And Mellon and others have done this. Mike Mellon is sort of the guy who started all this stuff. And regolith breathing. No one, to my knowledge, has addressed regolith breathing, and I'll bet there's not more than 6 people in this room who even know what it is. Who knows what regolith, who would like to describe regolith breathing? Anyone? Who thinks they know what it is? Okay, side issue, but we're here for fun. You might as well understand what Mars is like. Imagine a planet where the atmospheric pressure changes by 25% each year. Okay? And we know Mars does that. What people didn't realize is if you have a dry planet and the soil is porous, as you increase the pressure, you drive gas into the surface to whatever depth it's porous, which might be a kilometer. Who knows? So you could have a lot of gas at a moment. You could have some gas. Magnitude unknown, going down into the surface as the pressure increases that half of the year, and coming back out during the other half of the year. The regolith, which is a term for the broken up rocky surface of a planet, is breathing on an annual basis. And when it does that, past my fingers, changes the heat. that term, which occurs on Mars, I can guarantee you it occurs, to my knowledge, has been studied by no one. Got any graduate students who do a thesis?
Well, I think it relates.
The question is, how important is it? And that's another issue. But as far as I know, that aspect of heat transport, which occurs to some extent on Mars and does not occur on the Earth to any significant amount, is unstudied.
I don't know if now's the time to talk about science or not, but I mean, I've been intrigued for a very long time, going all the way back to the Viking, that these duracrusts, these sort of cemented layers, were several centimeters beneath the surface. They were kind of like one thermal skin depth down. And as this regolith is breathing, it's also, over a billion years, it's going to be transporting ions. And so vapor transport of material by the atmosphere and the thermal control of where that material might get deposited, I claim, could have an important relationship to where these duracrusts are forming and why they're not right at the surface and why they're not a meter down. They're a few centimeters down. And is that just a coincidence, or is it related to the thermal properties of the surface and this transport of gas in and out of the surface?
Well, the answer is simple. I don't believe in coincidences in geophysics.
Right, I agree.
Maybe in social affairs, but not in geophysics.
And everywhere we look, or many places you look, there's this crusted material that's just about that far beneath the surface. Anyway.
So anyway, that's just one line here. It's not included. Vertical transport of heat by gaseous diffusion is not included. Local rocks and shadows are not included because they involve lateral heat conduction or lateral heat transport. So not in here. Regional topography with shadows and radiative coupling is not in here. My topography is, it's tilted or it's a cone, that's it. And what those things see, another approximation we'll get to later, I'll mention now. When you got something like the sun shining on a tilted surface and it sees out a flat surface, the assumption KRC makes is that this surface is just the same temperature as I am, the slope here. Because remember, it only does one thing at a time. It has no other basis to make an assumption. You could maybe assume it's the average of all day or something. It assumes it's the same as me right now. It's approximation. Seasonal changes incrementally every sol or day. For those of you who are planetary scientists, the sol is the length of the, quote, solar day on that object. The way KRC goes is it moves the planet to some position in its orbit and spins. Then it moves it to the next position in the orbit and it spins, and so forth. It would actually not be too complicated to change it. That was done in the old days when moving it along the orbit was a significant calculation. Now it's trivial.
Does that invalidate it? I haven't thought about this, but does that invalidate it for something like Mercury or even the moon?
Eclipses, we have to come down to that. For the moon, you got to worry about eclipses, which it doesn't include. But
like if you're 3 days or a year.
No, well, it depends on how you set things up. Input parameters. I typically run at least 40 seasons in a year. So I'm moving 1/40th of an orbit. These are uniform in time, not in true anomaly. So they're not uniform in L/S, they're uniform in time as measured by a clock. I think it's a pretty small approximation. There is no constraint in KRC that doesn't allow you to make these as fine as you wish. However, at one point, if you make them really small, you have to do some tricks to make sure that it doesn't take over on you. Because here's the way KRC works. Imagine we're partway through. Initial conditions later. We're partway in. We've been here. We move to the next place in an orbit, and it spins. And let's imagine that these are separated by 16 sols. Okay? So it's going to spin here for 16 sols, but it doesn't. It spins one day, the first day, and records everything at midnight, because it starts at midnight, ends at midnight. It spins the next day, looks at how things have changed this midnight compared to the last midnight, and spins again. And by about the third day, it looks and say, okay, I've got 3 days. Are my changes really small now? Are they linear with time? Can I make a prediction as what's going to happen at the end of tomorrow? And it looks at, these are convergence parameters I was talking about. And once it thinks it's spent enough days to be able to predict 16 days, it stops. And it does a prediction based on a curve fit, an asymptotic curve fit to the temperature at each layer at each midnight. So that's the way it actually works. New season, spin until convergence, predict to the end of the season, go to the next. That's one of the intrinsic things in KRC that makes it fast for seasons, is because it doesn't have to calculate 16 days if it believes it can make a good prediction. Now, and so the answer to Josh's question is, there's a term in there for how many days I'm going to allow it to spin that is different than how many days elapsed in a season interval. Those are different. If the number of days I've allowed it to spin is longer than the season interval, you can get yourself into trouble. So if you actually wanted to do it every day, KRC has a way to do that. And I thought about this last night. I have not written it up, but there's a way to make it actually do every day just the way the planet actually does it, if you wish. And again, it's all in input parameters. So, but at the moment, that's the way it spins in place for a season. That's the approximation that's in KRC, and it's probably good enough for most uses. And Kim, that's what the production model is doing, is it's interpolating between the solutions at each of these explicit times in season. The first thing KRC does, or the production software, is if I wanted LCBS or a time, again it deals in time, if I want it on this particular Tuesday and I only calculate on Saturdays, it gets the prior Saturday and the last Saturday, linear interpolation in between, and makes that the global model. And then it starts worrying about where I am and so forth on the globe.
If you didn't want to have it predict forward to the, is that an input parameter as well?
It's implicitly there. You can force it to go to the last integral day. If your season step is, if your seasons are an integral plus a fraction, you can force it to go to the last integral day and then make a fractional day extrapolation, which will be extremely small. But that can be done. Let's see, where are we? Okay, geothermal heat flow. There is no geothermal heat flow in this model. It actually would be easy to add it. It's probably unimportant in virtually all cases, because geothermal heat flow is approximately 10 to the minus 6 of solar input, roughly. And we aren't we're not worried about microkelvin just yet.
There is one place where we are worried about it.
IO?
Permanently shadowed craters on the moon.
Yes. And
Not that I'm asking you to put it in, but
no,
it's interesting that you
yeah.
can actually worry about it.
Yeah, you can. And it would not be difficult to add that. And we can, it's not going to go on my list. If somebody wants to put it on a list, please do. Solar eclipses are no longer in KRC. They used to be. But I took them out as a complication was just difficult to support. And they would actually be fairly easy to put back in. Because KRC has been used to calculate lunar eclipse phenomena, things like that, and Jovian satellite eclipse phenomena in a prior version. But I'm only maintaining one version, so I may or may not have those old versions around, but it would not be hard to include if it were important. The equation of time is not in KRC. How many people know what the equation of time is? 1, 2, Interesting, none of the scientists, only programmers. Equation of time has to do with the fact that the actual length of a solar day varies through the year for an elliptical orbit. And the equation of time itself technically is the displacement of the time of noon, but what's really involved is the fact that the actual length of the day changes. That's not in here. So if you use this for asteroids with highly elliptical orbits, you may want to run a couple different day lengths and then compare the results. That would be the easy way to address that, Phil, if you cared. All right, so those things are not in there. And of course, this list goes on off the bottom of the page with things we haven't even thought about yet. Atmosphere model. Okay, third line is the important one. How do you start? KRC starts by assuming everything is in radiative equilibrium based on the average input of the sun over a day. It turns out that's a mess to do, but that's the way it does it. It's a good place to start. And then the atmosphere, any excess in radiation that goes into actually changing the temperature of the atmosphere, and the atmosphere affects the view from space. So KRC calculates a bunch of temperatures. The two that it outputs are the kinetic temperature of the surface. That's the physics. If you stuck a thermocouple on the surface, what temperature would you get? And what's called the planetary bolometric temperature. If you looked at the top of the atmosphere with a black detector that was black, that means it received radiation at all wavelengths, what apparent temperature would you see? So that includes the emissivity of the surface, the temperature of the surface, the emissivity transmission of the atmosphere and so forth, and they're all added up radiatively to see how much flux would you see with a remote observer. And that's one of the outputs because KRC is designed for remote measuring instruments.
I don't want to go into this now, but this is on my list of things I'd like to sort of make sure we're all clarified with what, you know, so in that model, what do you assume for clouds and dust and the temperature of the CO2 atmosphere and all that good stuff?
It's all here.
Right. I mean, so.
Yeah, that's what it uses. It uses the current opacity and current temperature, current visual and current solar opacities, which can be different by a fixed ratio. Those are what's used to calculate this. It's probably equation 43 or something in the paper. It's in there someplace.
Right, but I'm just saying, so, yeah. I mean, in you know, the test velometer, test spectrometer, Themis band 9, all mini tests, all of these have been used, and they have widely differing, they're not black, and they're not bolometers, and they're not, you know, so just want to make sure that in hindsight we did all the right things with all the right instruments and all the right analysis.
Okay. Hang on a second.
But not modifying at all for the effect of the atmosphere on band 9?
It's not going to be a big deal.
Okay.
Most of it.
I just want to make sure.
Guess what?
Yeah, exactly.
Just for those of you who aren't familiar with this, there's three things on here. The most important ones are actually these white curves, which are black body emission curves. The sun over here goes way up there. They're all normalized to 1. There's the sun, 270 Kelvin, 230 Kelvin, 145 Kelvin polar cap temperatures. Typical midday temperature, nice warm afternoon temperature on Mars. And you can see that the portion of the black body curve that's measured by these different instruments is very different. What is that? INTF? I don't know what that is. Anyway, I don't know where that came from. But these are the various instruments. Historically, these were the first two. Mariner 6, 7, and 9 had these two bands. Then the IRTM had these 5 or 6 bands, actually. This is the atmosphere band. The Mars atmosphere has a big absorption right here at 15 microns, so it's virtually opaque at this wavelength. TESS has a whole bunch of bands and a bolometer, which does this. Here are the Themis bands. Here's the mini TESS bands. It's got one bolometric band, right? One wide open or not? Nope. I don't know what that blue line is for then.
Well, mini test was sort of 5 to 50 microns.
It looks to me like I've got. Yeah, that's right. This is lower resolution, right? Anyway, the point of this, the point of this is, apart from the instruments, is I take all the flux that's coming out of the planet and say, what temperature would have, as a black body, have the same amount of flux as I have coming off the surface? Because I'm assuming everything's bolometric. So if you're looking at some other wavelength, you could be a little bit confused. But basically, most of the stuff we're dealing with is close to black body. I mean, there are whole theses and doctoral theses dependent on the fact that it's not a black body, and that isn't, but it's close to first order. So in terms of energy balance, this is what the bolometric temperature that comes out of KRC is the assumption that everything acts like a black body. And now if I can go back to roughly where we were. We haven't got there yet, have we? Well, we'll just go here and back up until it looks familiar. Here we are. Okay. Slopes and pits. It's actually, it's pretty straight. It's first order. Breaks a radiation field into 3 parts and assumes that the region around it is the same temperature it is. And then the rest is just geometry. What fraction of the solid angles do I have to deal with? I think we've been over most of this. Okay, the gravity and molecular weight of the atmosphere, which you need to calculate things like scale height, are input parameters. The default values are representative for Mars. They set the scale height. For those of you who aren't familiar with this. Okay, so the pressure varies as e to the minus z elevation over scale height. And here's the term for scale height. It's the temperature, the universal gas constant, the molecular mass, and gravity. So it just uses those things. We've talked about the 3 options for pressure. The dust capacity may vary with season, and it's scaled to the local pressure. So the amount of dust you have in the atmosphere depends on how much atmosphere is above you. So it's called the uniform mixing approximation. We've already talked about this. You can have a table for opacity, or you can use zonal climate. The ice cloud opacity does not scale with the surface pressure, which is probably realistic for Mars. Josh isn't here, but the ice clouds are typically ice opacity is typically at a relatively high altitude and about basically the same altitude every place. So it doesn't care what the local surface pressure is. One component may condense. This component is specified by its pressure-temperature relationship, the saturation temperature, what's sometimes called, the approximation I use is the Clausius-Clapeyron equation, which is a 2-term relation, which is very close to most gases. So it's plenty adequate. You can pick any gas you like. It happens to be pre-coded for, not pre-coded, the default input parameters are for CO2, but you can put other gases in there if you'd like. And the presence of any frost sets the surface temperature at the local saturation temperature, and it actually changes through the year. So in that sense, the polar cap, the saturation temperature depends on pressure, and the pressure changes through the year. The thing that's not included in this is a whole nother fraction of my career has to do with the accumulation of non-condensable gases, which I guess I won't mention any more than that. It's a kind of physics that occurs on Mars. Nobody thought it did. I forecasted it would 40 years ago, and it took them 30 years to discover it, but it's there. Neon and argon and nitrogen accumulate, get concentrated over the polar caps.
So I think it's worth mentioning, I mean, there are places on Mars where water ice will condense out at night.
Yes.
But your model ignores them because the
Yeah.
mass of water, the amount of energy it contains is just negligible.
That's correct. You could recode this to actually calculate water concentration. It would take not only a change in, it would take a little change in code, because at the moment it's the primary gas that condenses. We've talked about this. The frost albedo can vary with insulation, and it goes realistically to zero in a nice, smooth, exponential way, just as real materials do. I make an approximation for the downward going radiation from the atmosphere by assuming that that the atmosphere is at a particular temperature. And let me explain this one. This curve is the actual downgoing radiation fraction for a Mars atmosphere. If you had a 700 Pascal atmosphere, it's a little above Mars average. What happened is the following, and I guess Josh and Robin, you'll appreciate this, and everybody else will bear with me for a minute. I went and got an actual synthetic spectrum of a Mars atmosphere, calculated in gory detail by David Crisp. That is all of the lines for CO2, water vapor, other gas. And basically, he gave me the transmission of the atmosphere, 700 Pascal atmosphere, variable pressures and everything, as a function of wavelength. And then I imposed on one side of that, theoretically, a black body of some temperature and said, what fraction of the radiation gets through to the other side? What is the effective transmission of the atmosphere for a given black body? And this is actually the absorption of the atmosphere as a function of black body temperature. It peaks at about 0.13. And here's how it changes with temperature. KRC has an approximation. It just takes one number. At the moment, the default is 1,1, which is right here. You could pick any value you want, but KRC, a limitation of KRC, which could easily be changed and is on top of my list, is to make this thing a temperature-dependent fraction. At the moment, it does not depend on either the surface or the atmosphere temperature. It's just a fraction. And that's an input parameter, and it's 0.11.
It seems like a lot of things, especially with the atmosphere, we're trying to...
This is, clear atmosphere. This is no dust, CO2 only, or gas only.
Approximate for spectral effects without dealing with spectral effects, right?
Mm-hmm.
So it's always really tempting to want to start looking at other ways or adding the spectral aspects of this, but it gets way complicated and way tricky.
Yes, this particular one would be easy to do. Piece of cake, and it's probably top of my list. Is something that has a measurable effect and is really easy to do. So cost-benefit ratio here is pretty small. Okay, time for everybody to take a break. These are just stolen out of the paper. This is the fundamental upper boundary condition. This is the amount of energy that goes into the mathematical surface. And it's the amount of sunlight that's falling at that time in space times 1 minus the reflectivity of the surface, plus the solid angle times the thermal emissivity times the downgoing radiation. This is absorbed thermal radiation. Plus the heat flow, conductivity times thermal gradient into the surface, at the surface, minus the solid angle of the sky times the emitted black body radiation. That's the boundary condition. And then subsurface is the normal heat diffusion equation, which is this stuff right here, the left half. And normally represented by this term. This is what you normally see. K over rho c is the diffusivity, normally represented by a Greek kappa. It's always confusing because people use lowercase k and kappa in the same article, and they're almost indistinguishable without reading glasses. And a second order term, if you assume that the conductivity may be a function of temperature, as it now is, then there's another term here, which I assume to be 0 because this delta k delta z is a small number with depth, and delta t delta z is a relatively small number. So this number is very small. And it is assumed to be 0, and it actually only holds within a given layer. If you think about what's going on, it's only the magnitude of this within a layer at a given time that has any importance. So this part, this term here, partial t, turns into delta t. Now we got to do it numerically. And I convert this part over here into this mess over here. And this mess is due to the fact that conductivity can be different in each layer. And all these B's here represent the magnitude of delta Z. How thick is the layer? And so developing this equation, this is what's actually implemented in KRC. And it's for numerical stability reasons, it actually is done in 2 steps. First, you calculate the delta T for a given time step for all layers. And then you go back and apply it to all layers. You can't do it one layer at a time. You start confusing yourself. So it's done in 2 loops. And for the T-independent case, where temperature is now constant with, this is actually the code here for layer 2 to the bottom. Remember, the top layer is virtual, so I don't have to deal with it, because I'm going to fake its properties each time in order to manufacture the proper heat flow. So I calculate delta T for all the layers except the top one based on this equation. If you look at it and think about it from a computer programmer point of view, there are like 3 integer adds and 3 floating point multiplies and 3 floating point adds. It's only like 7 or 8 operations, which is a really small inner loop, and that was very intentional. Because this is the thing, as you'll see in a moment, this is where all the time is spent in the computer, is in this one line virtually. Now, if it's T-dependent, it's much more complicated, because all these K's up here, which are, if you assume they're constant, it reduces to this equation. If they're not constant, you got to calculate all this stuff every time. And it does that. So there's the first step, calculate all the delta T's, and then in a simple loop, simply apply them. So that's the inner loop of this routine. Here's some of the same stuff again. So I take this equation and I formulate it like this. A leading scale factor times the temperature of the upper layer, and another scale factor for the central layer, another scale factor for the lower layer. And here's what these scale factors look like. You see they're a mess of these terms. But if K, the conductivity, is temperature independent, and I've already said the layer structure is fixed at the beginning, these things reduce to simple constants. And it turns out that F2, the middle one up here, is equal to 1 minus F3, or minus 1 plus F3. So it reduces pretty simple. And that's what's at the core of KRC. And more equations. I put these all at once, trying to catch you before the afternoon when everybody's really down. This is a very important equation for KRC. The particular numerical method I use requires that this equation be satisfied. Delta time step size over the size of the layer. Now you can imagine this is all in SI units, if you'd like, all physical units, times the conductivity has to be less than a half. And this is just another way of expressing the same equation, only with the little b terms that I use internally. And the routine actually checks this for every layer, and it calculates a stability factor, which is by what factor have I satisfied this inequality? Am I twice as good? Am I 4 times as good? Once it gets to be 4 input parameter, maybe 4, maybe 2. Once it gets to be input parameter bigger, I double the time step as we go deeper into the system. Okay, two-stream delta Eddington is, this is a great supplication. Here's the delta Eddington part over here. The flux is equal to pi times input parameter plus 2/3 of another parameter. And basically this it's got, the delta Eddington just gives you 4 values for that. It gives you basically, out of the delta Eddington system comes essentially a normalized, at the top of the atmosphere, what's the fraction of diffuse radiation compared to parallel radiation? And at the bottom of the atmosphere, what is the fraction of diffuse isotropic radiation compared to parallel radiation? And you can then calculate the net flux at the top or the bottom of the atmosphere by just adding those 2 numbers. You add the parallel to the diffuse with the right sign, and that's all delta Eddington is, apart from the fact that there's this mess of equations you have to solve. So two-stream delta Eddington assumes the atmosphere has collimated light and diffuse light, isotropic. And it deals with those. And then, so the net amount of energy going into the atmosphere, there's the solar part, and this is a whole mess of stuff. This is, U naught is the cosine of the incidence angle, which on an atmosphere, you assume the atmosphere is flat, okay? No tilted atmospheres here. And so this is just the equation, a mix of, this is the upgoing radiation at the bottom, 1 minus the surface albedo, the collimated fraction. Sorry, this is at the top, this is at the bottom. The amount of downgoing radiation and so forth. This is what solar heating is of the atmosphere. Here's the infrared net heat flux of the atmosphere. It takes the temperature of the atmosphere. There's this e to the minus tau sub e is a part of a complicated numerical approximation I worked out that deals with what's the apparent opacity of an atmosphere in a hemispheric sense compared to the normal mathematical opacity in the perpendicular sense. There's a complex equation for that, a numerical approximation that I worked out. And then finally, this is the change in atmospheric temperature. It's the sum of the two, the visible and the, solar and thermal heat excesses divided by the specific heat of the atmosphere times its columnar mass amount. Very simple here. And then this is the term for planetary, the temperature you get. This is what the bolometric temperature is. The apparent bolometric temperature at the top is equal to the surface temperature times its emissivity times the Stefan-Boltzmann constant times the attenuation of the atmosphere plus the temperature of the atmosphere times 1 minus the attenuation of the atmosphere. And so you can write this equation this way, or you can write it that way, and this is what's actually solved in the equivalent equations. That's what's solved in KRC. Okay, now the programmers have to wake up. This is the essence of the numerical approach. We've already talked about the fundamental equation, finite differences. Oh, out of coffee. Okay. Here's the basic loop architecture. I'm going to refer to a thing as a run. When you put an input file in, that's a run. Okay. Put your cards through the wall. Something happens on the other side. The wizard pulls the handle. Out comes output. That's a run. A case is a particular set of input parameters. You've done all the change you're going to do the input parameters. You tell it to go, and it goes until it finishes, and then it comes back and asks you, do you have more input for me? And if you do, that's the next case. And you can stream cases. There's no limit to how many cases you can put in a run if you want to. There are practical reasons for making it, less than a few hundred, but there's no real limit. Okay, and then the next loop is seasons. KRC, you tell it what absolute time do I want to start at, expressed in Julian days. Everybody familiar with Julian days? Anybody familiar with Julian days? Okay. Its days started, like 7,000 years ago and counted ever since. So modified Julian days is that number minus some large number. In this case, KRC uses 2,440,000. And so that's what starts the time, and you give its increment in days or Julian days, both of which have the same length. And here, days is 86,400 seconds. It's a terrestrial day. And that day is, in fact, the only unit in all of KRC that's not System International. Everything else now in KRC is SI units, which is a change from the UCLA version. And so it has a season loop. You start at the first season you're given, calculate everything for that season. As I said, planet spinning in space. Final temperatures predicted at midnight at the end of that day, the final day, jump to the next season. And then within each season, it has a loop on latitudes. Because now we know where the planet is, we know where the sun is. Actually, the sun is specified by its distance, heliocentric range in astronomical units, and the subsolar latitude. Over what latitude on the planet does the sun appear to be at the zenith? Those are the only two things that you really need out of all this orbital geometry mess. And from where the subsolar latitude is, you can calculate what the insolation is through the day at a given place on the surface, whether or not you're in polar night, polar day, regular day-night seasons. It handles all those. Okay, the next one, days, is a bit of an artifact. Once you have a latitude, and there's a routine called tlat.f, and it does all this stuff. And once it's got the solar radiation set up, remember the solar radiation doesn't depend upon what KRC temperatures. It's only the infrared radiation that depends on temperatures. So you can pre-compute all of the solar stuff, what's coming down to the bottom, what's going up. You can pre-compute that before you do even think about temperatures. So all the solar stuff is done once in TLATs, and then it calls the next routine down, which is called T-day. And T-day starts doing days at a time. And a day is however many time steps you give it. Typically, I use 384, which is conveniently 16 times 24. KRC uses the term hours, but hour here in KRC language is 1/24 of a day. So when somebody says 3 p.m., sort of you have a feel for what it means. And it starts counting hours so that the 24th hour is midnight, which means that the first time step, if you use 24 hours a day, the first output time is actually 1 a.m. And the last output time is midnight. I could have said it the other way. For the first one is midnight and the last one is 23, but KRC works. The last time out is midnight, and the time size is however small you make an hour. And now I normally run with 48 hours a day. And the term hour is a synonym for how often we output values. Internally, it works with time steps. In this case, it's a number which you'll see later. Typically, I use 384, which is 16 time steps per hour. And I use 24 hours, so you get 24 output times per day. And so it runs for a day. And when it runs for a day, first it calculates, for each time step, it calculates all the delta t's. That's that top loop I showed a few slides ago. Then it goes back and adds all the delta t's, and then goes to the next time step. And it does that for however many time steps are in a day, and then it stops and says, okay, now what happened? And by what happened means how much did I change from the prior day? And at this point, it looks at average temperatures, midnight temperatures, does a whole bunch of sort of evaluation, and says, how big is my change? And if the change is small enough, I don't have to run any more days. I'm now going to hand it back to TLATS, telling it how many days I used, and TLATS will call a predictor routine to predict what it would be at the end of this season. And then those numbers are stored, and it goes on to the next season. Now, have you absorbed that? Would anybody, if I pointed at you and said, regurgitate it, could you? Okay. This is the fundamental way KRC works. Nested loops. At the moment, every number here is firm coded in one place in the main common statement. And if I've done this right, you should be able to go in and change any one of those numbers, recompile, and it will have smoothly propagated throughout the entire KRC program. And I'll show you that, hopefully I'll show you that in a minute. But these are the current numbers, 30 layers, 37 latitudes, 24 times 4 times 6, 64 steps per hour. That is slightly less than 1 minute for a terrestrial day, time steps. Output at 24 or 48 hours per day, up to 16 days to converge, up to 740 seasons. And some of these actually are fake limits. Depending on what mode you're running, you can go right past them. Most of them are actually firm-coded limits. And the reason is KRC keeps track of how it's doing so that it can go back and check, am I doing okay? Am I doing poorly? And it needs to store those someplace. And those are, Fortran, for those of you who are not aware, is not dynamic. Sizes and locations are compiled when you compile the program, and you cannot change them afterwards. That's why it's used for scientific computing. It doesn't have to mess with all kinds of relative indices and things. It's wired when you compile it, and it's a screaming fast after that. Yeah.
So maybe I'll bore everybody else, but I'm going to try to regurgitate just for my own sake. So I start off with 30-some layers, and let's say they're all isothermal.
Okay.
And the sun shines on the first one, and it heats up. Now, okay, so it's at a certain temperature, and all the other layers are isothermal. Then you go to this second layer and say, well, if this was a temperature above me and a temperature below me, heat conduction occurs, and so I'm going to move a little bit. And then it goes to the next layer, and the next layer, and the next layer. And it does that, and that is a single time step.
That's correct.
Then-
Almost correct.
Okay, let me keep going. Then it moves the sun a 16th of an hour. New input, but I still have that same set of temperatures. New surface temperature, conduct on, does that 740 times, or
Well,
384 times.
380, right.
And at the end of that, I have a temperature gradient that's something.
Yep.
Okay. Then it starts in the next day and does it again. Then it says, okay, at midnight I had this temperature gradient the first time around. Second time around I got this temperature gradient. Eventually those converge to where they're changing small amount.
Right.
You take that temperature gradient, put it into your predictor and said, it's changing this much per day. Well, wait, does it ever converge to where it says, this is, I've reached a convergence for a single day without changing the sun? You got to do that first, right?
Yep.
You just keep the sun here, because it starts isothermal, and it's going to eventually get to where, okay, without changing the sun, I've converged.
Yep.
Then I do change the sun, and I let it converge again.
Okay. Is your left hand time of day or season?
This is this is the sun.
Is it time of day? Is it moving? Is it twitching on a
Right, you're right.
time step or a season?
It's doing this. and it
Okay,
does
that's a
this.
time. That's okay. 1 day, half a day.
Okay, so it keeps doing that
Half a day.
until day after day, my temperature gradient at midnight is stable.
Yes.
Okay. So now it says I converge for a single day.
Okay. Well, actually, not strictly true, but close.
Okay.
We'll come back to that. Okay.
Okay, then I do move the sun to the next day. I move the planet to the next day,
The next season,
season.
because the next day is just the same as the prior day. Okay. Days. When you're at one season, that's the approximation I made. Every day in a season is identical in terms of the
Right.
boundary conditions.
Right, okay, but so I move this,
So-
I let the planet move to another season.
Yes.
I do the same thing again,
Yes.
and so the ending temperature profile at midnight is going to be slightly different from the last one.
Yep.
And you do that for 3 or 4 seasons until you can say, I can see the trend.
No.
No,
Okay.
okay.
There's the error.
So
The trend is between days at the same season.
between days at the same season. Okay.
You
Okay.
start a season, and you presume you have the profile from the last season. You start at midnight. You solve these equations for 1 day, 1 period, and you store them again. And after you've done that at least 3 times, it will start saying, am I converging? Remember, you got, in our example here, you got 16 days you could go, but you go 1, 2, 3, and you say, okay, let's look and see how linear. You're not trying to reach a static state. You're
Because it
trying to
won't-
reach a linear.
It won't be static.
Progression.
It can't be static.
Right,
It's
because-
changing. The sun is changing.
No, well, no, it could be. Sorry, back up here again. It's tedious, but it's important. Okay. A day is specified by how the sun crosses the sky above this point in a 24-hour period, a rotation of the planet. Okay, and so KRC will run from midnight to midnight, and at midnight it stores the profile. Actually, it does some other things in there too. It's actually on what's called a last day, which we'll come to in a minute. It actually also averages the temperature for the whole day at each layer. Basically, you get 2 outputs. Every day you get the temperature at midnight, and on a last day you get the average temperature. And it can look at, and I've forgotten exactly how this does because they're weighting of different convergence criteria. It looks at the change from day to day, that is midnight to midnight, and it looks at the, quote, last day. Now, the first time it looks at the last day, it does nothing. But it says, it looks at midnight to midnight, and And if midnight to midnight looks like it's progressing uniformly and small increments, then it says, okay, I'm ready to start the last day. And now it flips a switch that says last day, and it does it again. And on the last, now it's in the last day, it actually averages temperatures all day long, in addition to recording it at midnight. It gets to the end of last day, and, okay, now what does it do? Boy. It makes some test to compare midnight to midnight. And I think in there's also a test of whether or not the average temperatures have changed. There's 2 tests, and I've forgotten exactly how they're run. But they're both convergence tests. It's basically looking like, do I have a temperature, do I have a progression of profiles that is smooth and small? That's what you're looking for in numerical modeling. You're looking for answers where the progression is smooth and small.
That's for the entire day.
Yeah, and it's good. Normally it looks at midnight to midnight. At every midnight it makes some kind of an assessment.
So the assessment that's made, is it made on all the layers?
Yes.
Or is it made, okay. So
Yes, in a sense, I mean, step aside, famous mathematical statement. It is impossible to optimize more than one parameter at a time. Most people don't realize this. It is a fundamental mathematical statement. You can only maximize one function at a time. You can fool yourself into thinking you're doing a lot of other things, but realistically, one at a time, no matter how many dimensions you have. So what I do is I convert all of these things, like delta T from midnight to midnight, delta average temperature. I add them up in some way to make a single function that I'm trying to optimize. And I test that function. Is this function good enough? But remember, it's like binary in a machine, in a non-parallel machine. You can only do one logical test at a time. And after you've done all kinds of stuff, you come to one logical test that says, is it good enough? Which is what Phil's asking about. And if it's good enough, and it stayed good enough for the last day, I say, I'm done with this season.